Here's the answer to a couple of the problems about z-scores, which we did not get to in class on Monday, but we will be doing problems just like this in class on Wednesday. But I know some of you are working on problems now, and this will be helpful. This is related to the problem we did in class where we were marking our histogram with the mean and standard deviation. So let me just draw a picture of kind of a fake histogram to reflect what's going on in this problem. It says the carbon dioxide emissions of a group of nations has mean 8.4. So that's 8.4. And remember that we use our notation X bar for that. And a standard deviation of 1.2. So you want to imagine the histogram is here, has some kind of funky shape to it, kind of tails off. Same thing on the side. So the histogram of these answers is going to have this sort of symmetric shape. And then on the axis, we're marking off the mean plus 1 standard deviation, the mean plus 2 standard deviations, and the mean plus 3 standard deviations. And similarly, we're going to mark off the mean minus 1 standard deviation, the mean minus 2 standard deviations, and the mean minus 3 standard deviations. So the idea was that we expect pretty much all the data, 99.5% of the data is going to fit within those 3 standard deviations plus or minus from the mean. And the empirical rule tells us how many things fit within 1 standard deviation and 2 standard deviations and so on. So if I do mark these off, let me see if I can do that. The standard deviation is 1.2 here. So 1 standard deviation above would be 1.6. 1 standard deviation below will be 7.2. 2 standard deviations above will be 10.8. This will be 6.0. I think that's enough to get the idea of it. But anyway, I can mark those off on here. So so when we were talking about the empirical rule, we were talking about how the data spreads out according to the standard deviation. The idea of a z-score is to figure out how a particular data value falls within that spectrum. So the calculation that we do is this computation. We're going to take the value that they give us, the thing we're trying to find the z-score for. So here, let's say 15.8. So I'm going to take 15.8 minus the mean and divide that by the standard deviation. So that's the calculation that we do for z-score. Here's the value. This is always the mean, x bar, and this is always our standard deviation, s. So what this means on our graph is how many standard deviations above or below the mean we are. This number is, I don't know what that is. Hang on, let me get a calculator. All right, I'm good, I got a calculator. The result of this calculation is approximately 6.17. And so this z-score, this is telling us that that is the number of standard deviations above the mean. So this means we would interpret that as 15.8 is over 6 standard deviations above the mean. And that is crazy. Like we said, most of the data should fit within 3 standard deviations above the mean. That's here. So if I were to go another 1.2, that's 4 standard deviations, 5 standard deviations, 6 standard deviations. So 15.8 is way up here, almost off the realm of possibility. So that's that's how we answer the question. So we say 15.8 is 6.17, and again we round it that way just because they say to. This will be standard deviations above the mean. So that's what that means. If you saw a z-score that was 15.8, then there's something crazy about this value. This is so far outside of the realm of usual data that something weird's going on. So let's do something that's more normal. 1.3, we can already tell the second question B, 1.3 on our scale is way down here. Right, 1.3 would be way down here. So that's also going to be a crazy standard deviation, not within normal range. The one thing that's interesting about 1.3 is that when I do the calculation for the z-score, I always take my value, subtract the mean, and divide by the standard deviation. Let me do that on my calculator. I get approximately negative 5.92 standard deviations. But see, because this is negative, that means that my value is almost 6 standard deviations below the mean. So a negative z-score means that my score, my data point, is below the mean. So these are both really goofy values. 15.8 is unheard of for this data set. 1.3 is also unheard of for this data set. They're both around 6 standard deviations away from the mean. The other value, the 9.8, is the only one that's remotely normal. And if you draw a picture of what that is, you can see 9.8 would be about here, right? 9.8 would be about there. We can see from the marks that we already put on there that that's a little more than 1 standard deviation above the mean. Remember, here's the mean. Here's 1 standard deviation above the mean at 9.6. So 9.8 is a little bit above that. So this measurement ought to tell me that 9.8 is a little more than 1 standard deviation above the mean. Let's see if that's what we get. So I have z-score is 9.8 minus the mean divided by the standard deviation. And on my calculator, it says that's about 1.17. So that's how many standard deviations. And again, it's above the mean because it's a positive 1.2. Positive 1.17. And we can kind of tell from the picture already that that's where it's going to be, because as we noticed, it's we made our tick mark here not, at 9.6. Our tick mark is 1 standard deviation above the mean, and this value is a little bit further than that. So that's what z-score is doing. Z-score is telling you how far from the mean a particular data value is, but it's not telling you in just raw units. It's telling you in how many standard deviations away from the mean that value is. So here's another example of a problem using a z-score, and this uses height data. This is related to the problem that we'll be doing tomorrow in class. But they tell me, and I can just draw the picture, that the mean, wow, I did not mean to draw that in yellow. Hang on. So the mean height among these 288 women is 65.2 inches. And it tells me the standard deviation is 2.3 inches. So if I want to mark off 1 standard deviation above the mean, that'll be 65.2 plus 2.3. So that is 67.5 inches. If I mark off another standard deviation, that'll be another 2.3. That's 69.8 inches. And then similarly, so this is my mean. I'll make it dark. Similarly, I can go this way. If I subtract 2.3 from 65, I'll get 62.9 inches. And you can do this subtraction on your calculator. I can subtract another 2.3 inches and get 60.3. So here's my mean. And then I have 1 standard deviation above the mean here, 1 standard deviation below the mean, 2 standard deviations above the mean, 2 standard deviations below the mean. So now it's going to ask me about z-scores. What's the z-score for 60 inches? Well, 60 inches is here. Notice that's a little bit to the left of what I said was 2 standard deviations below the mean. So I can tell you right now that 60 inches is going to have a z-score that's a little bit smaller than -2. But let's do the calculation. Z is 60 inches minus the mean divided by the standard deviation. And so if we do that, we get a z-score of -2.26. oops, it says round to 1 decimal place in this case. All right, so it'd be negative 2.3 rounded to 1 decimal place. So my z-score is negative 2.3, which means we're a little more than 2 standard deviations below the mean, and that's exactly what we can see is happening here in our number line that we've marked off the standard deviations. The problem asks, what does the negative sign mean? That means that this value, the 60, is below the mean. So it's negative z-score means that you have a value that's smaller than the mean. And then, is this observation a potential outlier? Well, no. We said our outliers, using the standard deviation rule, our outliers are just things that are more than 3 standard deviations away from the mean, which means that we'd have to have a z-score of less than negative 3 or greater than 3 to consider a data value to be an outlier.